Welcome to Ask and Learn.
We have this series representation for 1 over pi, and for part A, we'd like to show that the series converges. And so let's go ahead and resolve this for part A. To do this, to show it converges, let's use the ratio test. Where we'll go ahead and set this term right here equal to an. So let me not write that whole thing out. So an will be this large fraction, but we will still have to do a bit of writing here. So notice that if we look at the absolute value of an plus 1 over an, we could drop the absolute value because the ANs are always positive. So in this case, let's go ahead and deal with this numerator here. So we replace all of the n's with the n plus 1. So that n factorial to the fourth becomes n plus 1 factorial to the fourth. And then we have 396, and then 4, and then n plus 1. Notice the parentheses here. And then we'll go ahead and divide that by an. So when we divide by an, we could go ahead and just flip this term here and multiply it to the red. So that'll be, as usual, as you've noticed when you've used the ratio test in the past. There we go. So we flipped an over and then multiplied it. So eventually we'll want to take a limit of this, but until we get to that point, we want to simplify as much as we can. So first thing I'll do here is, if we look at, let's maybe go in a different color here, blue. So this term right here, this is also 4n plus 4 factorial. And that would be the product of all the numbers all the way up to 4n plus 4. But before you get there, you cross 4n plus 1, and so on, until you reach 4n plus 4. And the reason I'm writing these additional terms out is because the first terms here, all the way up to 4n, that's 4n factorial. So we could go ahead and cancel this with this, and we're left over with this in the numerator. Similarly, I can go ahead and I could distribute this 26,000 term through the parentheses. So let me go ahead and do that. You'll see why shortly this is a good idea. So one of these terms should have an n, so this one will have an n. And what else can we do here? So now we look at, again, going to the blue, let's look at n plus 1 factorial to the fourth. So n plus 1 factorial, using the same idea as before, this can be written as n factorial times n plus 1. However, we also have an n factorial over here, and we're raising to the fourth power. So if we raise this to the fourth, get n factorial to the fourth, and then n plus 1 to the fourth. And so we could cancel this n factorial to the fourth with that one. And that'll leave us the n plus 1 to the fourth in the denominator. Now, what else do we have? So if we distribute this 4n plus 1 through, this is 4n plus 4. So we could cancel the 4n term here with the one down here, and that'll leave us with a 396 to the fourth power. And then one that didn't cancel out is this one here. So this also comes along. So we haven't taken any limits yet, just going ahead and simplifying as much as we can. So at this point, we have these products in the numerator, and these last two terms are very similar, but notice that they're different. This one in the top has an additional 26,000. Well, I'm running out of room here, so I'll go on to the next page, picking up where I left off. Okay, so now we can go ahead and from the previous page, we can factor out a 4. So I'll pull out a 4 from the 4n plus 4, and then the remaining terms, I'll leave them as they are. And the reason I'm factoring out the first term is, you'll see in a second, I'm going to be able to cancel with the term in the denominator. Because before we had n plus 1 to the fourth, now we can go ahead and cancel one of those with this one up here, leaving us with a 3. And then we'll still have our 396 to the fourth, and 1103, 26,390 n. So that was the only cancellation right there. And so now we're at this step. Let's see what we can do next here. We want to cancel, and we still have the 4 here. 4n plus 3. Okay, so the next step, I'll go ahead and distribute through the parentheses here. So what I'll do is I'll multiply this whole term out here through the parentheses. One will go to this, and then the other one will go to this term here. So this is going to be a bit more writing here. So and then the other one is where I distribute everything to this. So I'll just write that term in first so I don't get it. And then I'll write the remaining 4n terms. So 4n plus 3, 4n plus 2, 4n plus 1. So again, all we did was we distributed this term here that I'll circle in blue. We distributed this through the parentheses here. And you'll see shortly why this is a good idea. In the denominator, we still have our same term. Now, if we go ahead and break up this into two fractions, we'll be able to cancel a bit. So 396 to the fourth, n plus 1 cubed after cancellation. So we're splitting this into two fractions. In other words, we're going from something like this to this, and then I'm canceling afterward. And similarly, the other fraction. here we don't get to cancel like we did in the previous fraction. In the previous fraction, we were able to cancel out these two terms here, but not for the second term, but that's okay. So make note of this final expression here because I'll pick up where I left off on the next page. So next step I'll do here in the next page is I'm going to go ahead and factor out a 4 from each of these. So when I do that, I'll end up with a total of 256. So that's 4 to the 4th. Because I have 4 4s that I'm multiplying there. And after I take out the 4s, I have to factor it out from the parentheses. So here's my remaining expressions in the first fraction. And then for the remaining term down here, I'll just multiply that out. And similarly, do the same thing for the other fraction. So 4 to the 4th, 256. N cubed, and then also they're pulling out the 4. And then down here, I'll pull out n from this term. And then I still have n cubed, 3n squared, plus 3n plus 1. But we also have we still have this 396 to the 4th we have to deal with too. Okay, so let's go on to the next step here of the simplification. So at this step here, I could also factor out an n cubed here, so, and over here as well. So I will rewrite this. It's simplified here, so remember the whole point of doing all this is that so it's much easier for us to take the limit at the end. So we would still have this n cubed up here. So I guess I'll write that right now. But you can see in a second it'll cancel in the denominator because if I pull out an n cubed here as well, then I'm left with this. And so here we can go ahead and cancel those. That makes life a lot easier for us. And similarly over here, second fraction, you see that you have an n cubed there, so you can factor out 1 here and cancel. Yeah, here I have to write a lot of this stuff out, so this will take a moment. And then down here, n from this, I'll leave this part alone. And then here I pull out an n cubed just like previous step. Then don't forget the 396 to the 4th. So now we could cancel this. And then now we're at the point where we can go ahead and take a limit. If we take a limit as n goes to infinity and see what we have left over. Well, for the first term up here, what do we have? As n goes to infinity, that'll go to 0, 0, 0. So we just have a 1 here with a 256 over 396 to the 4th. So we're at the point now where we're completing the ratio test and taking that limit. Let me rewrite this out. 256 over 396 to the 4th. That's the first fraction, and plus. Now we go to the second fraction. So the n's canceled. These will all go to 0, so the parentheses all go to 1. And then you have this on top, but then the denominator goes to infinity because of this n here. So if you want, you could informally write this as and then this part would go to 0, and this is going to 26390 times 396 to the fourth. But the denominator is infinitely large, so the fraction goes to 0, and that just means that we're left with the first fraction, 256, 396 to the fourth, which is 4 over 396 to the fourth, which is definitely less than 1. So going on to the next page, so we conclude the series converges by the ratio test. And that resolves part A. Now we have a much shorter part B compared to this part A. For part B, we'd like to know how many decimal places of pi do you get. If you just take the first term of the series. Or what if you did the first two terms? So let's go ahead and answer that. So if we go ahead and take n equals 0 corresponding to the first term here, this would just be the 0 partial sum, which is just the first term. And we just go to our formula for an and plug in n equals 0. Into an here, and you're just left with this fraction, which is 2206 root 2, 9801. And remember, this is 1 over pi. So this is 1 over pi, because the series was given not as pi, but 1 over pi. So that should be an approximation. Sorry about that. So that means pi is approximately 9801, 2206 root 2. If we go to the calculator there, and we see that we get an approximation that's accurate to 6 decimal places. Now let's go on to the second part where we use the first two terms. So the previous part was using one term only. Now we go on to two. So this is where the first two terms will mean n equals 0 and n equals 1. So we have S1, first partial sum, which is A0 to A1. And then you go ahead and plug in n equals 1 into the 0 and 1 to the formula here. And there we go. Go ahead and simplify this a little bit. Just get common denominator up here. One second, let me see this. So this should be a 4 9, not a 9 4. Let me go back and erase this. Okay, so then take the opposite of that, the inverse, and get your pi, because remember, that's 1 over pi. So for pi, we get approximately 9801, 2 root 2, and then we flip this fraction here, and then we're basically finished. Now we would just go to the calculator, round this off, and see how many decimals of pi it gets you. So in this case, this one's going to give us much more. This time we're going to have 15 places. So 1, 4, 1, 5, 9, 2, 6, 5, 3, and then we have 5, 8, 9, and then 7, 9, 3. And then after that, it breaks off. So this is correct to 15 places. And that resolves part B.